In this video, I'm going to go over different ways to synthesize ethers. So just as a quick introduction to ethers, so ethers are compounds in which an oxygen is bonded to two R groups. So an example here, just in general, ORR, so you could have something like dimethyl ether, diethyl ether, and the diethyl ether is the one I'll use for a lot of the examples today when I go through different ways to synthesize them. Another quick thing I want to mention is crown ethers. These are cyclic polyethers. They have importance especially when it comes to binding metals because all the oxygens have lone pairs of electrons that can coordinate with the metal, and the metal is positively charged. Right, so what a crown ether looks like is it gets its name from being similar in appearance to a crown. One too many carbons there. Yeah, so there we go. That's like what a crown ether would look like. And it can range from just, 3 or 4 oxygens to a much larger number of oxygens in them. Now next there are 3 common methods of preparing ethers that I'm going to run through. Number 1 is going to be one that proceeds via an SN2 mechanism with an alcohol. So in this, we're going to start off with, methanol in this example. React the methanol with a strong acid. So here I'll choose sulfuric acid. The oxygen is protonated, so now there's 2 hydrogens on it, positive formal charge. It'll be attacked by another ethanol, right? And even though ethanol is a weak nucleophile, because the oxygen's been protonated, it's a fantastic leaving group. So this can come in, SN2 mechanism, and now I have the ether, but it's protonated, so it can react with another ethanol. And remember, we're in strongly acidic conditions, so that's the reason an ethanol can be protonated. And I finish up with my diethyl ether. Number 2 is going to be a Williamson ether synthesis. In this, I'll start off again with ethanol. But this time, rather than protonating it, it's going to be deprotonated with a non-nucleophilic base, so sodium hydride. So basically H-, that's going to come in, deprotonate. We'll get then hydrogen gas, and then an alkoxide. This will react with an alkyl halide, in this case chloroethane. It'll undergo an SN2 mechanism, and I am left with my ether. So the first one proceeded with acid catalyzed protonation, and this one's going to be a deprotonation, but we end up with the same product. Now a couple things to note here. The alkyl halide is usually either methyl or primary, right? If it's secondary, then it's likely to undergo elimination instead. And then tertiary, you won't get any reaction because of steric hindrance. So yeah, this will work best with a methyl or a primary alkyl halide. The last one is going to be an alkoxy mercuration demercuration. Now you may say this looks familiar because mercuration demercuration, or oxymercuration demercurization to be more specific, that is a reaction to reduce alkenes to an alcohol. This time, rather than using water as a reactant, we're instead going to use an alcohol as a reactant. And when the alcohol is a reactant, it will become an ether rather than an alcohol at the end. So if I have this alkene here, my reactants are, I got a mercury acetate along with ethanol, and then I use the sodium borohydride second. And what this will give me is the ethanol here will install at the more substituted position because this is Markovnikov. So I'm going to get this as my final product. So right, the ether, or the ethanol that installs is now the ether right there. And then we have a hydrogen add over here. The mechanism is identical to the oxymercuration demercuration mechanism, but it just uses, again, an alcohol instead of water as a reactant. So in my next video, I'm going to talk about what are some reactions that ethers can undergo.